Welcome back. On this video, we can discuss about the designing of logic circuit. Before that, we need to understand about the logic operations that we are going to implement. The logic micro operations manipulate the bits of the operand separately and treat each bit as a binary variable. Okay, so we need to understand micro operations. Logic micro operations consider each of the bits of the operand as separate binary variable. Okay, all logic operations can be obtained by means of three basic logic operations like AND, logic OR and logic NOT operations. These are the three basic logic operations. Using this, we can implement all other logic operations. Two selection lines can be used for implementing these operations. Okay, so basically using two selection line, we can distinguish four different possibilities. So along with this AND, OR and NOT operation, we can consider one more logical operation, Ixora operation. Okay, here we are going to use two selection lines. Using that two selection lines, we can distinguish four different logical operations. Okay, here we have only three, AND, OR and NOT. Okay, so we can consider one more operation. So that is, this XOR is considered along with this AND, OR and NOT operations. Okay, so this is the simplest representation of our circuit that perform for basic logic operations like OR, XOR and NOT operation. Okay, with two selection lines. When with value, the selection lines are represented as S1 and S0. With value 0, 0, this circuit perform this OR operation. That means this multiplexer select OR, logical OR operation as the output. With value 0, 1 for the selection line, it perform XOR operation. That is, this multiplexer select this XOR operation as its output. With selection variables value 1, 0, it perform AND operation, and with value 1, 1, it perform the complement or inversion operation. Okay. So, in order to design a logic circuit, we can combine this logic circuit with the arithmetic circuit that we have already learned in our previous video, how to design arithmetic circuit, and we have already discussed many such arithmetic circuit designing examples, right? So here we are going to implement arithmetic and logic circuit together. How it possible? We can design an arithmetic circuit and a logic circuit, and we can combine to form arithmetic and logic circuit. Okay, and in order to distinguish between this arithmetic operation and with the logic operation, we can use one more selection variable, this S2. Okay, this S1 and S0 actually used for distinguishing four different logic operations in case of logic circuit. And this S0, S1 and with the Cin input, in case of arithmetic circuit, using this S0, S1 and Cin, we can distinguish between 8 different arithmetic operations. We have already discussed about that in our previous videos. Okay, now again it uses separate single selection line, that is this S2. Using this S2, we can distinguish between arithmetic circuit and logic circuit. That means this multiplexer can select currently arithmetic operation or logic operation based on the value of S2. If S2 equal to 0, multiplexer chose this arithmetic circuit. And with S2 equal to 1, this multiplexer select a logic operation which is selected by this logic circuit. Okay, so for distinguish between this arithmetic circuit and logic circuit, we can make use the value of our selection line S2. Okay, so the basic designing principle of an arithmetic and logic circuit is that we have already mentioned about this principle. We need to design the arithmetic circuit first, then design the logic circuit. The third step, the important step is convert the arithmetic circuit so that we can modify the inputs of arithmetic circuit and generate various logic operations. This is the basic principle of our arithmetic logic circuit design. Generate arithmetic circuit first and understand what are the logical operation that we want to perform. Then try to modify the arithmetic circuit that already designed in order to implement the desired logic operations also. Okay, so this is not the efficient method of designing an ALU. Separately designing two circuit and comparing these two using multiplexer, this is not the effective method of implementing ALU. We need to implement arithmetic circuit and design the logic circuit and modify the existing arithmetic circuit in order to obtain the desired logical operations in it. Okay, so in order to perform that, okay, we need to understand the basics of our arithmetic circuit. We have already discussed about the design of arithmetic circuit. From that, it is clear that there we have used the parallel adder circuit for the implementation of arithmetic circuit, right? That parallel adder is actually implemented with the help of n different full adder circuit. Okay, if we want to perform arithmetic operations over an n bit data, then inside the parallel adder we need n different full adders, right? So this one is actually the output of full adders that we have already learned from our digital system, right? What is the output of our this one indicate the expression of our full adder output, that is with two input xi and yi with carry in value. The full adder circuit generate an output like xi xor yi xor ci, right? The input carries ci in each stage can be made to be equal to 0 when a selection variable s2 equal to 1. From this, we need to understand one thing. S2 equal to 1 means what we are going to perform now. We need to perform logical operation. Okay, so this value of 1 for this S2 actually indicate we are going to perform the logical operation. So whenever this S2 value become 1, automatically make this carry in value to be 0. Why? Because in order to perform logical operation, we don't want to consider the carry in and carry out values. This carry in values are actually used in case of arithmetic operation. So whenever start to perform logical operation, how to identify whenever we are going to perform a logical operation? This is based on the value of our S2. Whenever this S2 become 1, we want to perform any logical operation, right? So in that case, make the Cin value equal to 0. Okay, so based on that particular value, Ci equal to or Cin equal to 0, this full adder circuit expression is modified like this. But the Cin value becomes 0, this full adder output function become xi xor yi only. That means, suppose this a as xi xor yi, these much part together taken as a and ci is 0. Then what about the result of this a xor ci? A xor ci equal to 0 now. So a xor 0 means a and 0 complement is 1 plus a complement and 0. That means this one is a and this one is 0. A plus 0 is a itself. Right. So xi xor yi xor ci, here ci value equal to 0. So this term or expression is reduced to this particular form, that is function become xi xor yi whenever this ci value become 0. Okay, so keep this point in your mind. In order to perform a logical operation that is identified by the value of this selection line S2, whenever this S2 become 1, we need to make the ci value as 0. Okay, so that the output of our full adder is reduced to this xi xor yi. Okay, right. So now we can consider the function table regarding this logical operation. Based on the information that already discussed, in order to perform the logical operation, the selection line S2 must have the value 1. Okay, and we are going to consider for logical operation. Using that for logical operations, we can perform any kind of logical operations, right? So with value 1 0 0, xi and yi become ai and 0. This is actually the case of our arithmetic circuit. With S1 equal to 0, S0 equal to 0 and Ci equal to 0, xi become ai and yi is 0 and it perform the operation transfer operation. Right, now consider the same along with the value of S2. Whenever this S2 value become 1, make the Ci value 0 always, because here we are going to perform logical operation. We don't want to consider the Cin value, so here all or these 4 cases make this Ci value as 0. Right, so the exact output in this particular case is transfer operation. Now we want to get the expected operation. In this particular situation, the expected logical operation is OR. Okay, in our arithmetic circuit, in this particular case of S1 equal to 0 and S0 equal to 0, with Xi equal to Ai and Yi equal to 0, and with Ci equal to 0, it performed transfer operation. But we are expecting logical operation because now this S2 equal to 1. If is S2 equal to 0, it performs this transfer operation, right? Now consider the second case. With S1 equal to 0 and S0 equal to 1, with Xi equal to Ai and Yi equal to Bi, whenever this S2 value equal to 0, suppose S2 equal to 0, then our arithmetic circuit perform this particular full adder operation, that is Ixora operation. Okay, now this S2 equal to 1, it perform the same XOR operation, and the expected operation, logical operation, is also the same XOR operation. Okay, so consider the third case, S2 equal to 1, S2 equal to 1, then automatically Ci become 0. Okay, and with S1 equal to 1 and S0 equal to 0, with Xi equal to Ai and Yi equal to Bi complement. Okay, in this particular case, the full adder circuit perform an equivalence operation, that is XNOR operation. But the expected logical operation is AND. Okay, here it actually perform the XNOR operation. Okay, but the expected output operation is AND operation. That means we need to convert, we need to make certain changes over this input of this parallel adder or this full adder circuit and make this equivalence operation to equivalent logical operation, logical AND operation. Okay, now this is the case with S1 equal to 1 and S0 equal to 1. Okay, Xi equal to Ai and Yi with full of 1s, it perform the complement operation. Actually, the full adder output is this Xi XOR Yi. So, substituting this input value over this, it generates the complement of Ai. That is the meaning of this expression, right? Implement or substitute this input over this full adder output, it generates output like this. First case, Ai itself, that means transferring the input A to the output of our full adder. And this one actually indicate the XOR operation. This is XOR operation and transfer the complement of AI. Right, but what are the required logical operation correspondingly? What are they? Or, logical XOR, logical and logical NOT. These are the four logical operations that we are going to implement, which is clear from this particular diagram. These are the four operations that we are going to implement. Okay, so based on that, it is clear that this XOR operation and NOT operation, which is directly possible from our arithmetic full adder circuit. Okay, with this particular selection combination S2 equal to 1, S1 equal to 1, S0 equal to 1, with Ci equal to 0 and Xi equal to Ai and Yi equal to 1, automatically this full adder output become equal to the output of our logical NOT operation. So, which is directly possible with our existing arithmetic circuit. Once more possible, this XOR operation is also possible. Consider the second case, S2 equal to 1, S1 equal to 0, S0 equal to 1. With Xi equal to Ai and Yi equal to Bi and Ci equal to 0, by substituting this input over this full adder full adder output function, it generates the XOR operation itself. The expected logical operation XOR is XOR, and the obtained operation is also the same XOR operation. Okay, so two expected logical operations are directly available here by making changes or making proper input substitution over this Xi and Yi of our full adder. Now our task is to convert this transfer operation to required logical OR operation, and this this particular equivalence or XNOR operation to logical AND operation by making changes over this input combination Xi and Yi. Okay, once more, our task is to convert this transfer operation to logical OR operation and this equivalence or XNOR operation to logical AND operation by making certain changes over this input Xi and Yi of our full adder. Okay, how it possible? Consider this particular case. AI XOR BI complement is AI, BI complement, all complement is BI itself, right? Plus AI complement and BI complement. That is AI XNOR BI. That is actually, this is the explanation for this particular case. How it is obtained here, this XNOR expression. Substitute this AI and BI complement over this XOR function, that is the full adder output function. Substitute this to input. Then it become AI, BI complement, all complement is BI itself, plus AI complement, BI complement. This is actually AI XNOR BI. That is represented here. Obtained full adder output now become XNOR operation with these two inputs. So consider next case, S1 equal to, S0 equal to 1 and S2 equal to 1, this particular case, right? AI with Xi equal to AI and Yi equal to 1. Substitute this input over this XOR function, full adder output function. Now it become AI complement and this 1 plus AI into 1 complement is 0. That means this term only, AI complement, right? So this particular full adder output become this function Fi equal to AI complement with this input values like Xi equal to AI and Yi equal to 1. These two are XOR and NOT are directly available from our full adder output function with this same input combinations. Okay, our task is to generate this Our task is to convert this transfer operation to logical OR operation and this equivalence operation to logical AND operation by making certain proper changes over this xi and yi input of our full adder. Now consider that. The expected logic operations are OR, XOR, AND, NOT, etc. This XOR and NOT directly available from our given input set. Okay, now we are going to implement or we are going to generate this logical OR and logical AND. The transfer, we need to convert this transfer operation to logical OR operation first. Then we need to convert the equivalence operation to logical AND operation. So consider this case. S2 equal to 1, S1 equal to 0, S0 equal to 0. With this particular combination of input xi equal to ai, yi equal to 0, they expect the actual full adder output become ai. Just a transferring of our xi input to the full adder output. But the required logical operation is OR. So in order to get the result of this logical operation as an output of our full adder, what we want to perform or how to change this input. Change the input of our full adder circuit from this AI to AI logical or BI. How it possible? In order to change this AI to AI logical or BI, instead of this AI input to this XI, make this AI XI input as AI plus BI. Right? Instead of passing this AI value along to this XI input of our full adder, substitute AI plus BI as an input to this XI input. Then this transfer operation become AI plus BI. That means the expected logical OR operation is obtained by making this changes over this xi input. Instead of passing ai along to this xi, transfer ai plus bi to this xi. Then this full adder circuit transfer ai plus bi, that means ai or bi to the function output or the full adder output. This transfer now become equivalent to our logical OR result. Okay, the next case is conversion of this XNOR operation to the logical AND operation. For that, how to modify this XI input? For that, instead of applying AI along to the XI input, substitute another term. That is, instead of substituting this AI along to XI, substitute AI plus BI complement. So, by substituting this input, AI become AI plus BI complement and YI become BI complement itself. So, substituting this to the full adder output function, that is AI plus BI complement XOR this BI complement, it become AI plus BI complement and BI complement, all complement is BI itself, plus AI plus BI complement, all complement and BI complement. Okay, so while expanding this, the terms like this, AI BI plus BI complement and BI plus AI complement, what is it actually? While taking this complement inside, this become, applying the De Morgan's law, this become AI complement and this BI complement, all complement become BI, right? Then the external BI complement too. So this term become AI BI. This becomes 0. This again becomes 0 because BI and BI complement is 0. So the result is equivalent to AND operation over AI and BI input. So in order to make this XNOR operation to the logical AND operation, instead of substituting AI along to the Xi input of our full adder, substitute AI plus BI complement as an input to the Xi input of full adder and Yi input as BI complement, so that the output function generate a result, that is this AI and BI, which is equivalent to the result of our logical AND operation over AI and BI. Okay, so these are the modification required over the arithmetic circuit in order to generate the logical operation for different logical operations like logical OR, logical AND, XOR and NOT operation. Right? So, now consider the full function circuit that include arithmetic operations and 4 logical operations. With S2 equal to 0, the first 8 combination indicate the arithmetic operation that we have already learned. And the next 4 operation with value S2 equal to 1 and Cin. We don't want to consider the value of Cin. Always consider the Cin as 0 in case of logical operation. Okay, we don't want to consider the Cin, Cout value in case of logical operation. That is why this don't care here. Okay, when S2 become 1, we want to perform this logical operation. So, with S2 1, 1 0 0, it perform logical OR operation, 1 0 1 XOR operation, 1 1 0 logical AND operation, 1 1 1 complement operation. So, this is the complete function table of our arithmetic and logical operations. Okay. So, this is the case of expressions that indicate the circuit of our arithmetic and logic circuit. Okay, we have previously learned about the design of the arithmetic part of ALU only. Now it consider both the arithmetic and logic part together. So the circuit expression is like this. Okay, this is the case when S2 equal to 1, our circuit perform this operation. That means the input for Xi and Yi is like this, so that it perform for different logical operations. With S2 equal to 1, the Xi and Yi input like this. Xi is AI plus S2 into S1 complement S0 complement Bi plus S2 S1 S0 complement Bi complement. And the Yi input like S0 Bi plus S1 Bi complement. The same here in this arithmetic part also. When S2 equal to 0, the Yi part is same. Okay. In case of arithmetic operation, Xi input is always AI itself. Okay. This Yi is actually what it is? This is S0 Bi plus S1 Bi complement. We have already derived this expression. Okay. In case of our 4-bit arithmetic circuit design, we have already derived this expression. The same is possible here in logical circuit also. But we need to consider this Xi part. This is entirely different in case of logical operation. So consider this expression. Okay. With S2, S1, S0 is of the form 1, 0, 1. Okay. With 1, 0, 1, we need XOR logical operation. Okay. So, XOR operation means here with these selection values S2, S1, S0 is of the form 1, 0, 1. This Xi become AI plus this term become S2 is 1, S1 complement, 0 complement, 1, S0 complement, 1 complement is 0. So, this term becomes 0. Plus, here it is 1, 0, 0 complement. Here S1 is 0. So this term again become 0. So in this particular case, xi become ai and this yi become what? S0 in this case is 1. 1 into bi plus S1 is actually 0. So this term becomes 0. 1 and bi is bi itself. So in this particular selection case, 101, xi become ai and yi become bi. So substituting this to our full ladder circuit, the output is ai XOR bi. The same expected logical operation XOR is obtained now. Consider the second case. S2, S1, S0 is of the form 1, 0, 0. So with 1, 0, 0, expecting logical operation is OR here. Okay, so consider this. AI plus substituting this value, S2 is 1, S1 is 0, S0 is 0. S2 is 1. 1 plus 0 complement 1 into 0 complement and 0 complement bi. That is 1 and bi is bi itself. Okay. Then this term S1 is 0. So this term become 0. Now xi become ai plus 1 and bi is bi. So here in this particular selection case, xi become ai plus bi. And this yi become, this term is 0. This S1 is actually 0. So this term is again 0. And this term is also 0. S2 complement, 1 complement is 0. So in this case, xi become ai plus bi and yi is 0. Right? In this case, the full adder output function xi XOR yi generate ai plus bi XOR 0. That is ai or bi. The output of this expression. While expanding this, we get an output like this, ai or bi. The expected logical OR operation. The same result of our logical OR operation here. Okay. The next case, S2, S1, S0 equal to 110. Okay. In case of 110, the expected operation is logical AND operation. So consider this expression. AI plus S2 is 1, S1 is 1. 1 complement is 0. So this term becomes 0. Here again, S2 is 1, S1 is 1. Sorry, S0 complement is 0 complement is 1. So 1 and bi complement is bi complement. So here xi become ai plus 1 and bi complement is bi complement. Ai plus bi complement. Right? Then this yi become, what is this? This term is 110. So S0 is 0. 0 and bi is 0 itself. Next this one. S1 is 1 here. S1 is 1. 1 and bi complement is bi complement. So the inputs are like xi equal to ai plus bi complement. Yi is bi complement. So substitute this value, this input value over our full adder function a XOR b, then ai plus bi complement XOR bi complement. Xi to be ai plus bi complement and bi is this bi complement. Sorry, yi is this bi complement. Right? So while performing this, it generates an output ai bi complement. The same result of our logical AND operation. Okay, so consider the next case, S2, S1, S0, 1, 1, 1. In that case, xi become ai. The two remaining terms become 0. So xi become ai itself. Okay, and yi become what? S0 and bi is bi itself S1 and Bi complement become 1 and Bi complement become Bi complement. Okay. So Bi plus Bi complement is 1. So Yi term become 1. Xi become Ai and Yi become 1. Okay. So Ai XOR 1 become Ai itself. And also Zi become S2 complement. 1 complement is 0 into Ci is again 0 here. So Ai XOR 1 become Ai itself. So the all four expected logical operations are possible with this given expression. Xi is like Ai plus S2 and S1 complement and S0 complement Bi plus S2, S1, S0 complement Bi complement. And Yi is S0 and Bi plus S1 and Bi complement. And Zi is S2 complement and Ci. And with S2 equal to 0, we need to perform the arithmetic operation. We have already derived this input combination. Xi need to be Ai, Yi need to be S0 and Bi plus S1 Bi complement. And Zi must be Ci. Okay, so consider the diagram based on the previous expression. Xi, these are 2-bit ALU, arithmetic and logic circuit, with Xi and Yi input and are connected, right, based on our this expression. Okay, and this Zi input is connected based on this value. Okay, so this is the complete circuit diagram for our arithmetic and logic circuit together. Okay, and this marked here based on this given expression. Okay.